Hi guys, welcome to the second class of electricity. We in the first class have already discussed about the basics of electricity. We had discussed charge in details. So today we are going to study slightly higher concepts and we'll be solving quite a few problems also, numerical problems as well. So let us begin with the first slide. So, um, guys, a very important part of electricity is electrical current as well. So, what is electrical current? Is something that we are going to study in this slide. Okay. So, we understand that the charges are capable of flowing within the conductors. Okay. So, conductors are all those materials which are capable of allowing the flow of charges through them, and these charges, they flow in the form of electrons within the materials. This is exactly what is given in the first line. All right. Further, guys, electrons flow in a conductor which is generally made up of a metal, and it is capable of losing electrons, and hence these are the electrons which actually move inside the conductor. They do not move helter-skelter. They move from their higher concentration to their lower concentration. So electrons will always move from their higher concentration to their lower concentration within the conductor. Okay. So what is electrical current? Electrical current is the rate of flow of electrons through any cross section in a conductor. Okay. So let us assume that conductor is a cylindrical pipe. Okay. So the number of electrons that are flowing out of the mouth of the pipe in some given period of time will be called as the electrical current. Electrical current, it is denoted by capital I. Okay. Further, guys, electrical current, it is denoted by this particular, or it can be calculated by this particular equation, that is I is equals to Q upon T, or I is equals to the quantity of charge that flows through the cross section of a conductor per unit time. Okay, this is referred to as the electrical current. The SI unit of electrical current is ampere. What is it? It is ampere. Okay. Also in the previous class we had studied that Q is also equals to Ne, or the quantity of charge is also equals to number of electrons that are lost or gained by any material into the charge on a single electron. So by replacing this value in the first equation, we actually get I is equals to N into E divided by T. Okay. Okay guys, so far we have seen two formulas for calculation of electrical current. One is I is equals to Q upon T, and the other formula is I is equals to N into E divided by T. So these two formulas will be used for solving our equations or numericals which are based on electrical current. Okay. Moving forward, guys, the SI unit of current, as I've already told you, is ampere. Okay, 1 ampere is equals to 1 coulomb divided by 1 second. Okay, I've already told you that coulomb is a very big unit of charge, and similarly, since it is directly proportional to the unit of current, so 1 ampere is also a very big unit of current. All right. So some other units of current which are regularly used are 1 milliampere. 1 milliampere is equals to 10 raised to power minus 3 ampere. 1 microampere. 1 microampere is equals to 10 raised to power minus 6 ampere, which we'll be using in the numericals moving forward. All right. So let us solve a few numericals based on. Guys, the first numerical says that a current of 150 milliampere flows through the circuit for 2 minutes. All right. So we need to find the amount of charge that flows through this circuit. Okay. So let us see what all is given. It is given that the current is equals to 150 milliampere. 150 milliampere can also be written as 150 into 10 raised to power minus 3 ampere. Okay. Further, guys, the time that is given to us is 2 minutes. Let us convert this time from 2 minutes into seconds. So 2 into 60 seconds is going to make 120 seconds. This is the final time. All right. We need to find the value of Q over here. Okay. So let us use the following equation. We know that I is equals to Q into T. Okay. So if we reshuffle this equation a little bit, we are going to get Q is equals to I into T. Okay. So by putting all the given values in this equation, what do we get? We get Q is equals to 150 into 10 raised to power minus 3 ampere into 120 seconds. So when we multiply 150 by 120, we get 18,000 into 10 raised to power minus 3. Now you can see that 10 raised to power minus 3 can be cancelled with these three zeros. So finally the amount of charge, or the quantity of charge that is actually flowing through the circuit is equals to 18 coulomb. All right. Let us solve another very important question. So the second question is that a total of 6 into 10 raised to power 46 electrons are flowing through any current carrying conductor when it is connected through an external power supply for about 20 seconds. So in 20 seconds, how many electrons are flowing? 6 into 10 raised to power 46 electrons. So the questioner is asking us that we need to find the value of current in the conductor. Okay, so how do we do that? Guys, it is given to us that here the number of electrons that are flowing in the conductor are 6 into 10 raised to power 46 electrons. All right. Further, guys, the time is about 20 seconds. Okay. So we know what is already known to us is that the charge on a single electron is about 1.6 into 10 raised to power minus 19 coulomb. Okay. Also, what is known to us is that so another thing that we need to find out in this question is that what is the current that is flowing through this particular conductor. Okay, so for this we know of an equation. We know that I is equals to Q upon T, and we also know that this is further equals to NE upon T. So if we put all the values in this equation, what do we get? We get I is equals to, instead of n, I've written 6 into 10 raised to power 46. Instead of the value of E, I've written the actual value of E, which is 1.6 into 10 raised to power minus 19. And instead of T, now I've written 20 seconds. Okay. When I go ahead and cut all these numerical or numeric values, what do I get? See guys, 6 divided by 20, I actually get 3 over here. Okay. And 10 divided by 10 raised to power 46, or 10 raised to power 46 divided by 10, I actually get 10 raised to power 25. Okay. Further, I can get this cut this 10 raised to power 25 with 10 raised to power minus 19. Okay. So the value that I get is 3 into 1.6 into 10 raised to power 26. And this turns out to be, guys, 4.8 into 10 raised to power 26. Okay. So now we know that the current that is flowing through the circuit is actually 4.8 into 10 raised to power 26 ampere. Okay. So which is a very big quantity of current that is flowing through the circuit. Okay, guys. So I want you to pause the video once again, try to do these questions, okay, so that the concept of electrical current is very clear to you. You not only have to do these two questions, I'll be giving you set of some other questions at the end of the this video also. I'll be sharing it on our groups, all right, so that you can, do it at home also, practice this concept a little bit more, all right. Moving forward, guys. So, current can be measured by a device which is called as ammeter. Okay, so this is what ammeter actually looks like. Okay, and an ammeter is generally connected in series with the circuit. So what does series looks like, guys? So let's say this is a single wire that is coming out of the circuit, or which is in the circuit. So on the same wire, if I connect something which is consuming the electricity, which is referred to as the load. Okay, so both the ammeter as well as the load, they have to be on the same wire, they cannot be on a different wire. Okay, so that is when we call them to be in series, or we say that they both are in series with each other. However, the concept of series and parallel will become clearer to you when we read the concept of resistance. All right, so for now we just need to understand that anything which is on the same wire as that of the load, okay, which is actually consuming electricity, will be called as being in series with the load. Okay, so ammeter is always connected in series. Okay, and there is a reason for why it is being connected in series, which will be explained later on. All right, okay. Further, guys, ammeter has negligible resistance. So why do we need to have negligible resistance? And by the way, what is resistance? The way when we move, so friction, it kind of stops, or it impediments, acts as an impediment to my motion. It tries to oppose my motion. In the similar way, when current flows through any conductor or non-conductor, so resistance always tries to resist the flow of current. Okay, so it is actually acting like an obstruction to the flow of current. Okay, so ammeter has negligible resistance. The reason being, we want maximum current to flow through this. Okay, so that we can measure the maximum amount of current that is actually flowing through the entire circuit. We don't want to cut upon any current. Okay, so that is why we should have ideally a very high, a very low resistance of this ammeter, so that maximum current can flow through it. Okay, and we can measure current very accurately also. Okay, okay guys, further, conventionally you need to remember that the direction of flow of current is usually opposite to that of the flow of electrons. Okay, or you can also say that it is in the same direction as the flow of positive charge. This is something that we are going to study in the coming slides. Okay, so just hold your horses over here. All right, so let's move forward, guys. So before we understand the mechanism of flow of current, it is very important for us to first understand that what an electrical cell actually is. Okay, electrical cell, it's a device that is capable of changing some form of energy, such as chemical energy, nuclear energy, or let's say radiant energy, which is nothing but the solar energy, into electricity. So if any cell or any instrument is capable of converting any other form of energy into electrical energy, I'm going to call it as an electrical cell. All right. Okay. So generally speaking, electrical cell is capable of performing chemical reactions in two separate compartments. Okay. Now, what is happening in these two separate compartments? See, there is one compartment, okay, in which electrons are continuously being consumed. Continuously they are being siphoned off. Okay, so this particular terminus is called as a positive terminus. The reason being that this is always, it always has deficiency of electrons. Okay, electrons are never to be found over here, because as soon as they are created, they are continuously taken away. They are continuously taken away from this particular compartment. So there's always a deficiency of electron, and hence it is net positive in nature. This is referred to as the positive terminus of the battery. Okay, moving further, guys, there is another compartment in the cell also, wherein electrons are continuously being formed. They are again and again being replenished. They are being formed. Okay, so there is a net negative charge on this compartment, and this is also referred to as the negative terminus of the battery. What is it called? It is called as a negative terminus of the battery. I have already spoken about the fact that electrons, they always flow from the their higher concentration to their lower concentration. Isn't that so? I've already told you that. All right. So let's just look at how the cell actually appears to be. So you can see that there is a positive terminus of the battery, wherein a reaction is taking place. Let's say there is a non-metal which is actually in need of electrons in order to satisfy its octet. So it is going to consume all the electrons, get converted into a negative ion or an anion. Okay, so this is how electrons are being consumed over here. So there is always a deficiency of electron at this terminus, and hence this is positively charged. Okay, then there is another terminus which is called as a negative terminus, where you can see that there must be some metal, okay, which is actually, in order to satisfy its octet or its duplet, it is actually losing electrons. Okay, so when it is losing its electron, okay, so it is becoming a positively charged ion, and these electrons are getting accumulated in this particular part of the cell. Okay, so this is net negatively charged. So this is the positive terminus of the battery or the cell, and this is the negative terminus of the cell. Is this much clear to you? Okay, guys. Now, what I was telling you before, just before we discuss the diagram or the construction of this particular battery, I was telling you guys that um, electrons, they always flow from their higher concentration to their lower concentration. Okay, so that essentially means that electrons should flow from this negative terminus to the positive terminus, but actually this does not happen. The reason being that there is a barrier that is between the negative compartment and that is between the positive compartment of the cell, okay, which actually stops the transport of electrons within the cell. Okay, so now what happens? So when the cell, so the cell now has to be connected to some wires. Okay, so this has to be connected to some wires. Okay, and when it is connected through these wires, which is actually nothing but a conductor, so it is through the conductor that the electrons actually flow from the negative terminus to the positive terminus. Okay, so it is actually through the conductor that the electrons flow from the negative terminus to the positive terminus. Also, another thing that is interesting is that in case I put any electrical equipment over here, let's say it's a bulb, or let's say this is a tube light, okay, which is capable of making use of electric current. Okay, so if I connect it within this electrical circuit, that is going to get lit up. Okay, that's going to get lighted up because electrical current is going through that. All right, did you understand this much, guys? So this is all about the cell. Now we are going to study about how the electrical current actually flows within the conductor. So this will be referred to as the mechanism of flow of electrons within the conductor. Okay, so let us go through that as well. Okay. 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 So guys, when the conductor is not connected to any kind of a battery, okay, over here or over here, so what happens is that the electrons or the free electrons, they move here and there. They move randomly just about anywhere. Okay. And this is not a very productive movement. Okay. Because the electrical current, which is probably created by this electron, is cancelled out by this electron. Okay. So the opposing electrical currents, they cancel out each other, and hence there is no net flow within the correct within the conductor that actually takes place. Okay, so it is very, very important that if we want some current to flow through this conductor, it should be connected with a battery. The moment we connect it to the battery, you are going to see over here that there is a positive terminus of the battery and there is a negative terminus of the battery. So this is the positive, the longer line is actually the positive terminus and the shorter line is actually the negative terminus. So you see that the electrons within the conductor, after getting attracted to the positive terminus, they actually start flowing, all of them, they start flowing towards the positive terminus. Okay, so it is the positive terminus which actually pulls these electrons towards itself, and this is how electrical current is actually generated within the conductor. Okay. Okay, guys. Further, we need to understand that this pull is maintained because in the positive terminus, the electrons will always get consumed, and hence it will always be net positively charged, and it is going to attract the oppositely charged electrons towards it. Okay. On the other hand, at any place within the conductor, if there is depletion of electrons that is occurring, so these depleted electrons are again replenished by the negative terminus of the battery. The reason being that negative terminus is showing a reaction wherein many electrons are getting formed, and we know that electrons always flow from their higher concentration to their lower concentration. So the moment the electrons they get depleted from any place, they will again get replenished by the negative terminus of the battery. Okay. Okay, guys, moving further, the passage of the current continues till the time the chemical reagents or the reactants within the cell do not get completely consumed or exhausted. Okay, that essentially means that the current is going to flow till the time the cell is not dead. Okay, so this is the mechanism of flow of electrons within the conductor. And we know that when electrons move in a conductor, so electrons which pass the cross section of conductor in any period of time is also capable of generating what? It is capable of generating current also. Okay, so this will be responsible for creating current also. Okay, further guys, 2 3 other interesting things coming up in the next slide. So what is the direction of flow of current and electrons? Okay, so before the discovery of electrons, protons, I told you there was already a concept of positive and negative charge which was in place. The term positive and negative charge was given by a scientist whose name was Benjamin Franklin. Okay, now guys, if I tell you that there is a positive one and if I tell you there is a negative one, which quantity would you say is bigger? You'll obviously say that positive one is bigger than negative one. Okay, and that was also the mindset in earlier days also. Okay, so anything which was positively charged was considered bigger or was considered more important. Okay, so earlier it was thought that electrical current or the direction of electrical current is the same as the direction of flow of positive charge. We now know that positive charge is present in the nucleus, and it is incapable of getting out of the nucleus. The reason being that the protons they are held very strongly within the nucleus. So the only thing which is capable of showing movement is actually the negative charge, or it is actually the electron. Okay, so guys, now if I say that the movement of current is taking place in the direction of that of the positive charge, so can I also say that the movement of current is taking place in the opposite direction as that of the electron? Is there anything wrong in saying that? Okay, so that is the reason why conventionally the direction of current is always from positive to negative terminus, and the direction of electrons we now know is always from negative to positive terminus. We are aware of all this, right? Okay, guys. So, guys, in the diagram which is given over here, you can see that the direction of flow of electrons is from the negative terminus to the positive terminus. So they are actually flowing. If you see this green arrow, you follow the green arrow. So it is flowing along the green arrow from the negative terminus to the positive terminus. Okay, so just like this. Okay, however, the flow of current is represented by this red line or the red arrow. Okay, and the current is actually flowing from the positive terminus to the negative terminus like this. Okay, so we must always remember that the direction in which the electrons flow, the current flow in the direction opposite to that. All right, okay guys, let's move forward. How can we ensure that current flows continuously through the electrical circuit? I can ensure it by actually connecting it to a cell or a battery. if I connect it to a cell of or a battery which has inexhaustible source of chemical reagents, which is capable of producing electrons at one end and which is capable of consuming electrons at the other end, the electricity will flow continuously through the conductor. Okay. Now, what is the explanation behind this? The explanation behind this is that the chemical reactions within the battery, they actually develop something which is called as a potential difference. Rings a bell? Okay. So it generates something which is called as a potential difference across its terminals. Okay. And it is this potential difference which actually drives the current across the conductor that is connected with the battery. Okay. Guys, I told you the direction in which the electrons they move between the two materials are dependent on a concept which is called as electrical potential or potential difference. Okay. And similarly over here, this particular line is also saying that the battery is creating something which is called as an electrical potential, which is actually responsible for the movement of current through the conductor. Okay, so what exactly is electrical potential? And this is a very, very crucial question that we asked in the previous class also. So this is going to be revealed just right now. All right, so let's move forward, guys. Now this is a very Okay, guys, so let's discuss the concept of electric potential. We know that the end of conductor with the higher density or higher concentration of electrons, it forms the negative terminus, okay? And the end which has lower density of electrons or lower concentration of electrons is referred to as the positive terminus. This is something that we have studied in the construction of battery also, or the cell also, okay? Further, guys, it's generally the positive terminus that is considered to be at higher potential. Okay. So this is a convention that we use. Okay. One of the reasons for this convention could be that anything that is positive is considered to be greater than anything which is negative. Okay. However, there is another very important reason why the positive terminus of the battery or the cell is considered to be at the higher potential. Okay, the reason is this, that it is the positive terminus that actually attracts the electrons towards itself. All right, so it is the positive terminus which is actually creating a force of attraction for the electrons to be drawn towards itself. So in turn, it is responsible for the passage of electrons and then in turn the passage of current through the conductors also. Okay, so that is the reason why the positive terminus is supposed to be at a higher potential. Okay, okay, so that was a more logical explanation, okay, of why positive terminus is considered to be at a higher potential. Having said that, we still haven't really understood what potential is all about. Okay, so let's look at this very simple diagram. Over here we see that there is a unit positive charge in the center, and this is surrounded by these concentric circles. So these concentric circles, they actually denote the electric field. Electric field is the space around any charge where the force of repulsion or force of attraction due to that particular charge can be felt by any other external charge. Okay, so it is the space around any charge or any quantity of charge wherein if any other charge comes in, so it is either going to feel a force of attraction or it is going to feel a force of repulsion. Another thing that we see in this diagram is that there is another quantity of charge, that is Q plus, okay, which is kept at infinity. You can see that both these charges are positive in nature. Okay, so guys, we studied in the properties of charges that the like charges, they repel each other. That means positive charge is going to repel the positive charge. So in case I want to bring this particular positive charge, which is kept at an infinite distance and which really does not faces any force of attraction or repulsion from this particular charge over here, okay, if I want to bring it inside the electrical field, I will really have to push it in order to bring it inside the electrical field of another unit positive charge. Okay, that means I will have to perform certain work in order to send this particular quantity of charge, which is kept at infinity, inside the electric field of this particular charge. Isn't that so? Okay, so this is what is denoted by the electrical potential. Okay, so let us read the definition of electrical potential. Electric potential V at any point inside the electrical field. Let this point be A. Let this point be A. Okay. So electrical potential at any point inside the electrical field is equal to the work required to move a particular quantity of positive charge from infinite distance to a specified point within the electrical field of another unit positive charge. So guys, it is equal to the ratio, or electric potential is equal to the ratio of the work that is done, okay, the work that is done in bringing this particular charge inside the electrical field of another positive unit positive charge. Okay, and obviously if you are trying to bring the positive charge inside the field of another positive charge, so we'll have to do certain work against the repulsion. Okay, okay guys, so this is what is electrical potential. Another very important diagram coming up now. So guys, as you are going to increase the quantity of charge either over here or either at the center of this field over here, okay, the force of repulsion is going to increase. So the force of repulsion is going to increase. So in that case, I will have to perform more work in order to send this particular charge inside the electrical field over here, okay, of another unit positive charge. So that essentially means that greater the amount of charge, that is either this particular charge or this particular charge, okay, greater will be the potential of that particular or greater will be the electrical potential or the work that is required in bringing that particular quantity of charge inside the electric field of another quantity of charge. Okay, slightly tricky concept guys. Okay, so I want you to again go through this video if it is required, okay, so that you can again get the concept of this thing. Okay, and in case this is not very clear to you, you can always call me up. Okay, you can read up a little bit about it and clarify your doubts with me at least. Okay, okay, let's move forward guys. So electrical potential is measured in a quantity which is referred to as volts. Okay, there is a numerical or there is a equation by which we can actually calculate the amount of electrical potential. So electrical potential at any point A is equal to the work done in moving charge from infinite distance to A, okay, divided by the quantity of charge that is moved. Okay, so it is essentially equals to work done upon quantity of charge. We know that work done is calculated in terms of joules. Okay, so the unit is same as energy. Okay, and then this has to be divided by the quantity of charge, and the unit of quantity of charge is actually 1 coulomb. So 1 joule per coulomb, or 1 joule divided by 1 coulomb, is equals to 1 volt. Okay, so this is the unit of electrical potential. Okay guys, so a potential of 1 volt means that 1 joule of work is being done to move 1 coulomb of charge from infinite distance to a point within the field of another unit positive charge. Okay, okay guys, so related to the concept of electric potential, there is another very important concept which is called as a potential difference. So let's see what exactly is potential difference. Okay, okay guys, so guys, over here you see that there is another unit positive charge at the center over here, and all these concentric circles, they represent the electric field, where if any other quantity of charge tries to come inside this electric field, it is going to face a force of repulsion, which is denoted by these arrows over here. Okay, so guys, let's suppose that this particular quantity of charge is already present inside the electrical field. Okay, so it's facing certain force of repulsion over here. Now let us say I try to push this particular quantity of charge further inside the electrical field. Okay, so now it is trying to get closer to this positive unit of charge. Okay, so it's going to feel a greater force of repulsion closer to this positive charge. Okay, So that means if I want to move any quantity of charge within the electrical field of another quantity of charge, I will still have to perform certain amount of work. Okay. And this amount of work that is being performed to push this particular quantity of charge from one point to another point within the electrical field of another unit positive charge, this is referred to as the potential difference. What is this referred to as? Potential difference. Okay, guys. So let's move forward. So potential difference, it is the difference in the electrical potential between the 2 points, or it is the amount of work that is done in moving unit charge from one point to another point in the electrical field of another charge. Okay. Further, guys, potential difference is also mathematically denoted as delta. Delta means a little difference. Okay. Delta V, or the potential difference. Okay. And delta V is equals to the potential at the final point minus the potential at the initial point. So it is equals to the potential at the final point where the charge has been pushed to minus the potential at the initial point. Okay. Okay, guys. So let's move forward. So let us assume that the potential in at the position B is equal to VB, and VB is equals to work done in bringing the quantity of charge from, let's say, infinite distance to the point B divided by that particular quantity of charge, and VA is equals to work done in bringing that particular quantity of charge from infinity to a distance A, okay, divided by that quantity of charge. Okay, so what is delta V equals to? Delta V is equals to VB minus VA. Let us put these two values in this equation. So we get delta V is equals to VB minus VA, or delta V is equals to WB divided by Q minus WA divided by Q. Okay, so we get delta V is equals to WB minus WA divided by Q. So can I say that WB minus WA is equals to delta W, or the difference between the work or the total work that is being done? Yes, I can. Okay. So the final formula becomes delta V is equals to delta W divided by Q. Okay, guys? Okay, guys. So this is the final formula for potential difference. Now let us see another very important and exciting concept. Okay, let us now associate electrical potential with potential difference. Okay, so here is the diagram. So guys, we need to understand one thing, that when any quantity of charge is kept outside the electrical field at any infinite distance, okay, then it does not have any electrical potential, okay, or V infinity, V infinity is equal to 0, okay. So the potential at infinite distance is equals to 0, okay. Okay, so now if I try to bring this quantity of charge inside the electrical field of this unit positive charge, so what will be the potential difference? Okay, so let's move forward, guys. So the potential difference in this case will be equals to the final point at which I am trying to bring the potential at the final point at which I am trying to bring this quantity of charge, which is VA, okay, minus V infinity, okay, because VA is the final position and V infinity is the potential at the initial position, okay. We also know that V infinity is equal to 0. So let us just substitute this value in this equation, and now we get that delta V is equals to VA minus V infinity, or it is equals to VA minus 0, or it is simply equals to VA. So we know that when I try to bring any quantity from infinite distance to any point inside the electrical field of another positive charge, then the electrical potential is equal to the potential at that particular point. Okay, the reason being that the potential difference is equals to VA minus V infinity, and V infinity becomes 0 in this equation. So the potential difference or the potential, it becomes actually equals to the potential at that particular point. Okay guys. Okay, so moving forward guys, look at some other important units of measurement for potential difference as well as for electrical potential. We know that electrical potential as well as potential difference is measured in terms of volts. Okay. Now there are certain other units of measurement for the voltage also, and this is 1 kilovolt. 1 kilovolt is equals to 10 raised to power 3 volt. Then there is 1 millivolt. 1 millivolt is equals to 10 raised to power minus 3 volts. Then there is 1 microvolt. 1 microvolt is equals to 10 raised to power minus 6 volts, so on and so forth. Okay. There is an instrument which is called as voltmeter, which is used to measure the potential difference. Okay. And this is the SI unit of potential difference is also called as volt. Okay. Further guys, voltmeter, you must remember, is always set in parallel across 2 points where the potential difference has to be measured. Now the reason for why it is actually connected in parallel and not in series is something that we are going to study after studying Ohm's law or after studying the concept of resistance, because that is when series and parallel is going to get more clear to us, and that is when we'll understand that how the potential difference and how the current actually varies when the connection is made in series or in parallel. But as of now, you need to remember that the voltmeter is always connected in parallel, and the ammeter is always connected in series. Okay. Okay guys, moving forward. So this is how the parallel connection is made guys. So if this is the conductor, it is in between point A and B. So if between the point A and B, the conductor is on a different wire, let's call it as L, and the potentiometer or the voltmeter is on another wire, let's call it as L1. So then they will be called to be on in parallel to each other. Okay. Okay guys, let's move forward now. So we also need to remember that the purpose of voltmeter is not to measure the current. Okay. So we don't unnecessarily want any amount of current to pass through it or very little amount of current to pass through it. Okay. So I need to build a lot of obstruction, or I need to have a lot of obstruction in this device in order to not allow a lot of current to pass through it, because the purpose of this device is not to measure current. Okay. So it has very, very high resistance, and this is exactly what is written over here, that it has high resistance so that negligible amount of current passes through it. Further guys, the term volt has been given to voltage, which is another term which is also used for potential difference also. Okay. Okay guys, so let us now do a few numericals. Okay, and let's move forward with this concept. So the first question is that how much work is done in moving charge of 3 coulomb across 2 points having a potential difference of 15 volts. Okay, so let us see what all is given to us in this question. So it is given that the potential difference is equals to 15 volts. The amount of charge is equals to 3 coulomb. So the work done, we have to calculate the total work that is being done over here. So guys, the equation is actually delta V is equals to delta W divided by Q. Okay. So if I reshuffle the equation a little bit, I'm going to get, so I shift this Q over here. So I get that delta W is equals to delta V into Q. So delta W is equals to delta V into Q. Okay. So guys, putting the values that are known to us in this equation, we get, so delta W is equals to 15 volts into 3 coulomb, which is equals to nothing but 45 joules. So guys, this was the solution. I want you to please go ahead and practice this. Pause the video, practice it, or probably note it down after seeing the video, and then attempt it on your own. Okay. Also, I'm going to share few more questions with you also so that you have clarity whether you've understood the concept or not. Okay. In case there is any doubt, please feel free to call me. Obviously, this is not a classroom based training where I can understand whether you are able to understand or not. Okay. So I want you to have open channels of communication with me and just call me up. Just let me know if there is any doubt and I'm going to solve it for you. Okay. Moving forward. So the second question is calculate the potential difference between two terminals of a battery. Okay, if 100 joules of work is required to transfer a charge of 20 coulomb from one terminal of the battery to another coulomb of the battery. So it says that there are two terminals of the battery we are aware of, which is the negative and the positive terminus. Okay, what they are saying is that in order to drive a particular charge from one end to another end, the amount of work that is being done is 100 joules. Okay, and the quantity of charge that is being transferred is actually 20 coulomb. Okay, so you need to calculate the potential difference between the two ends. Okay, so let us calculate this one. Guys, again, what is given to us is that delta W is equals to 10 joules, quantity of charge is equals to 20 coulombs. Okay, the potential difference is not known to us. We need to calculate the potential difference. What is the formula for potential difference? The formula for potential difference is equals to work done upon quantity of charge. So potential difference is equals to work done upon quantity of charge. By putting these values in the equation, we get delta V is equals to 100 joules divided by 20 coulombs, and this turns out to be 5 volts. Simple, straightforward question. Okay, next question, guys. Now, the next question says that how much work is being done in moving a charge of 2 coulomb from a point at potential 18 volts to a point at potential 128 volts. Okay, so now guys, again, you need to remember that let us just take a simple example that there is a battery. Okay, and one of the ends is at the potential of 128 volts. Okay, and the other one is at a potential of 118 volts. Okay, now the charge of 2 coulomb is being moved from 118 volts to 128 volts. So the initial potential is 118 volts and the final potential is 128 volts. Okay, and the quantity of charge that is being moved is how much? 2 coulomb. We need to calculate the work being done in order to move this quantity of charge from one potential to another potential. Okay, so let us see how do we solve this one. So guys, given is that the final potential is or the VB is equals to 128 volts. The initial potential or VA is 118 volts. The quantity of charge is equals to 2 coulombs. Okay, and the work that is being done is not known to us. Okay, so the equation is equals to delta V is equals to delta W upon Q. Okay, if we reshuffle the equation, we get delta V into Q is equals to delta W. Okay, so I can write this as delta W is also equals to VB minus VA into Q. Okay, so if the potential difference is not directly given to you, you need to calculate the potential difference by finding the difference between the initial potential, the final potential and the initial potential. Okay, so we are going to calculate this potential difference and put it over here, the value over here. So guys, let us solve this further. So now by putting the values in the equation, we get delta W is equals to 128 minus 118 volts into 2 coulombs. This is equals to 10 volts into 2 coulombs, which is equals to 20 joules. So guys, 20 joules of work is being done in order to actually push a particular quantity of charge or 2 coulomb of charge from 118 volts to 120 volts. Simple, guys. Okay, so we've solved quite a few numericals in this video. Okay, I want you to please pause the videos in between or probably after watching the video solve these questions once again. I'm also going to give you a little homework on our group also. Okay, so please solve these. Okay, and I understand that there is a lockdown for coronavirus. Okay, however, it is not like you can go outside and play. Okay, so I want you to, this is class 10th, so I really want you to focus on your studies also a little bit. Okay, and please start studying as soon as possible, okay, because it's then there'll be a lot of backlog also. Okay guys, so stay inside, stay safe, please watch these videos, solve all the questions. All right, okay guys, so this is Dr. Nehul Saxena signing off. Please take care. Bye bye.